My name is Dr. Shobboshachi Sen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For Computer Science and IT, bouquet is something. For Mechanical, Civil, it is different. For Electrical, Electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the Computer Science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that we'll be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we'll be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Well, warm welcome to this class on Physics 2. This is my 9th class in a row. Now in this class, as we have been doing, we have been exploring the most recent technology, okay, that is the quantum technologies and its application, okay. And the basics, the ABCDs of quantum technologies lies in the ideas of quantum mechanics. So what you are learning, starting from based on your first year knowledge, okay, you are developing now. The first year you learned all the theories. We are now developing all the applications of quantum mechanics, called Quantum Mechanics 2. So I've already taken 8 classes on Quantum Mechanics 2. This is going to be the 9th class, and again for another interesting class, because here
you will again learn few more techniques of dealing with quantum mechanics problem. As you know, quantum world is a microscopic world. In this microscopic world, your language is mathematical language. Your weapon is mathematics. So we have been because my matter is a mathematical function psi. So we have been everything doing more on. We have been doing a lot of mathematics. Okay, a lot of techniques of mathematics we have been applying for the purpose of the class. So today also switch on your mathematical button of your brain so that you can do many things very wonderfully. And as I often mention that at the beginning of the class, I'll remind you that what you have been doing. You see, this is very basic. Okay, this is my 9th class, and this is myself, as you know. That every class I remind you this issue. Every day, if you see all my video lectures, you will notice. First thing I clarify what you do in my class of quantum mechanics. 4 things can happen in nature. A matter may be matter-like collision. Newton is there to help you. Now, next is wave may be wave-like superposition. You know, have learned interference, etc. Another is wave may be particle-like photon concept, which you also know from my class. Now, which you do not know, or which you are learning rather now, is a 4th aspect, that is the wave nature of matter, which is an idea of de Broglie, is improved by Division-Gerber experiment. And today you know that this is the situation. In my class, electron will move, so it should have some velocity, some momentum, all the material property. But you are not happy, or you are not focused on this discussion, electron moving like a matter and colliding. We are not interested about that because classical physics deals with those things. Quantum mechanics means we are talking about the wavy nature of the matter. Okay, how this wavy nature comes up is it is coming up from the idea. Okay, it is coming up from the idea that wavy aspect of the matter of probability concept. Because electron is too small an object, if it orbits around, if it moves, okay, for us it is difficult to locate the electron. So at a given point we take chance to find out the electron. Chances will vary, variation will make a wave, that is a wave of chances or wave of probabilities as described by a function psi. Psi square gives the probability of finding the particle. Total probability is 1. We can calculate psi in a real physical problem. Suppose an electron is moving around the nucleus, we can calculate psi in a real physical problem, as you know, from by solving a differential equation. That equation was proposed long back in 1926, namely the Schrödinger equation, which is second order first degree partial differential equation, where from problem to problem V is going to vary, and our objective will be to calculate the function psi. Okay, now after you get psi, you can do many more things. Suppose I have got 3 electrons moving together. Okay, so if they move, they should have some momentum, should have some kinetic energy, should have some potential energy if they are under some force. So all the parameters of motion will be there. So the technique that I told you, because electron is a microscopic particle, and to us electron is represented by a mathematical function psi. So our idea was that entire mechanics, all the parameters of motion, which are called dynamical variables, we can generate out of psi. So how do we generate? We can extract out of psi. So we have attacked psi, we have knocked psi, we have asked question to psi. How did you ask question to psi? We have explored with psi, that psi, tell me the momentum, psi, tell me the kinetic energy of the electron, psi, tell me the potential energy of the electron, and it is expected psi will answer to our question. Okay. So how does psi answer? Psi is a function of mathematics. So technique was that anything you wish to measure for that purpose, we have asked some mathematical queries to psi. How do you interact with psi? You interact with psi in the language of some mathematical operation. So for every dynamical variable you wish to measure, there lies a mathematical operator. And this is a list of operator you know from the last few days. For every variable, I requested to make you remember that position and time has got no separate form. Momentum is a first differentiation operator. Kinetic energy is a double derivative operator. Potential energy is also function of x. Hamiltonian is summation of kinetic energy and potential energy, like that. And energy other than mechanical is in general I star del t. So this has been the operator form. What is their job? If you have to get momentum, operator of momentum should be talking with psi. So it will be a first derivative of psi. So how does it act? okay, this example I have been giving you for the past 2 days, I request you today to only to look at e to the power ikx type of function. Suppose I have solved Schrodinger equation and that is my psi. So if you satisfy an eigenvalue equation, there is operator acting on the function gives you back the function which is happening there with both with momentum and kinetic energy. Then and only then you satisfy an eigenvalue equation, and then and only then you can measure that particular constant variable. The constant appearing, that is in the case of momentum hk by 2 pi, and in case of kinetic energy h square k square by 2m. Okay, that type of thing. So those things are the measured value of the kinetic and momentum or kinetic energy. And I told you these are structured. In a problem, h card is constant or h is a constant. And if you put the right value of mass and k, etc., you will get the actual momentum or actual kinetic energy of the system. So it's a new technique. We are doing it mathematically because we cannot see the matter.
Okay, usual power failure has disrupted a bit. So because we could not see the matter, so therefore we have to rely on mathematical idea, mathematical brain of us. We are using the ideas of mathematics. There is a concept of mathematics called eigenvalue equation to calculate the momentum or kinetic energy or any dynamical variable for that matter. So try to realize it, keep it in your brain. We are not doing anything by ourselves. We are relying on the mathematics concept. Okay, we are doing it mathematically. Okay, so we are using some ideas of mathematics. Okay, just like here eigenvalue concept is utilized. If you satisfy eigenvalue equation, then and only then you can measure, otherwise you cannot measure. That is the message. Similarly, as it progressed in our discussion, these concepts will come on later on also. Okay, this will come up later on. This concept will come up later on also, particularly this problem, a particle is moving inside a well. This is one example of calculating eigenvalue. You see, it is difficult for you to see the matter. So you take chance to find out the matter. Okay, chances are describing by the function psi. From psi you can calculate energy. It is a real life example. Okay, one of the fundamental problem of quantum mechanics is this much. Okay, so basically you can do many things. Okay, so now if you move forward, you see all the, and after that we got, for if an operator has got multiple wave function, has got eigenfunction, then you can see this beautiful theorem called superposition theorem. The cats are actually representing something special. Okay, zeros and one concept. Okay, dead or alive concept. Okay, they're called Schrodinger cats. I discussed it in length, so I'm not getting into that details, because that superposition principle, the 0-1 idea, is utilized in quantum computation. Okay, at 0 and 1 is not just accepted state, their mixture is also an allowed state. Okay, so this is the ideas how it is applied. Now after that we ended up, I discussed about a wonderful theorem called idea called orthogonality relationship, by which we solve some problem also. That is, orthogonality of two or more function is given there. You can see there, conjugate of one of the function and the other function. Okay, it makes the orthogonality relationship. Okay, I told you the mantra is that if I am integrating same function and its conjugate under this type of limit, I will get non-zero result. And if that means square of a function like that, and if you get, say, take two dissimilar functions, say sine, cos,
x sin x, x cos x like this, you'll get 0 result. Okay, so that is the message. So this is a huge mathematical advantage. Okay, just like as you can see here, if you are taking two different function, you will get non-zero result. Zero, you will say only sine, only cos means one function is 1, another function is sine or cos. X sin x, x cos x, sine cos, like that. That is going to give you the 0 result. Okay, and we get the normalization condition, you can see also, which has been already applied in solution of the problem. And now after that we have applied another idea of mathematics, that is called commutation bracket of the operator. Okay, two or more than two operator, okay, two operators can commute if they follow this relationship. Okay, AB minus B, A and B are the two operators. Suppose A may be X, B may be P. So their commutator bracket is XP minus PX. So if you replace the value of the X and P in operator form, then you will get that whether you will end up with a 0 or you may not end up with a 0. If you get 0, you say the operators are commuting. If you do not end up with 0, that means you say they don't commute. Now there are some physical meaning. If they commute, you can measure those variables together. And if they don't commute, you cannot measure them together. So again, you see, commutator bracket is a mathematics concept. What you are doing, you are utilizing that idea of mathematics again for the purpose of measurement. What measurement? Measurement of two data together. Whether you can measure two variables together or not, that prediction you are doing. You are not doing directly, you are only predicting by using the prescription of mathematics. If two operators commute, in an experiment it is possible for them to measure two together. And if they don't commute, you cannot measure them together. So it has been justified also with some real calculations. Say position and momentum are not commuting. Time and energy was not commuting. So it is nothing but Heisenberg's uncertainty principle, who long back told that you cannot measure correct value of position and momentum together, energy at a given time correctly. So these are all obeying, and also we have shown some good positive cases also, like in position and energy you can measure together. Okay, kinetic energy, potential energy you can measure together because they commute. Now today, what we will do actually, we will move from, so we have been happy with psi is the most important parameter now in our class, representing the matter electron maybe. But if you see, majority of the problem that I discussed is only on a single particle moving, mainly single particle. Maybe one or two cases I have shown more than one particle, but majority of our focus have been to talk about how do you generate data. Suppose what is the position of one electron, what is the momentum of a single electron, what is the kinetic energy of a single electron. So we have been mainly focusing on how do you get this data for only one electron. Okay, how do you achieve this data for only one particle? But nature, nature it does not deal with one particle. Okay, it may be the commutator bracket for a single particle. How do you get the two data? That is commutator bracket. For a single particle, how do you get momentum or energy? That is eigenvalue equation concept. Now basically, nature does not deal with only one object. For example, suppose an electron is moving around the nucleus. This is one object problem, and that is the case of hydrogen atom. But apart from hydrogen atom, everywhere you talk about many electron case. For example, say we'll be talking about semiconductors, which are solids, where crores of electrons will be moving together. So now, if you have to describe your system, you should not restrict yourself only with one particle problem. So quantum mechanics cannot stuck at one particle problem. It has to move. It has to move to many particle cases. As I have shown in the initial video, if you see the total video, you will notice as you move from one particle to many particle, so some basic concept actually gets changed. Okay, how does the basic concept change? You see the example, you'll realize. This is one particle moving. Okay, one particle at its momentum, you can see. Now if I consider many particle moving, this case. So at the left hand side with black and white, it is the case of single particle position, single particle momentum, and because of uncertainty, you can see it's a beautiful example of uncertainty idea also. You see, when momentum is diverging, you are getting position, and when you are getting position, you are losing momentum. Okay, like that. Okay, or opposite. When you are getting momentum, you are losing position, becoming uncertain. You see, and now momentum. You see the picture left hand side. Okay, you see when you are getting all the momentum, no position is lost. Okay, and now when you are getting position correctly, you see your momentum is lost. So beautiful demonstration. Now you see, please spend some time in realizing this thing. Okay, But this black picked line where you are showing both position and momentum pictures together, that is the case of one electron, one particle. Now what we wish to do, from one particle we wish to many particle case. Suppose 3 electrons are moving together. And again, these are all mechanics problem. I wish to know their position, I wish to know their momentum, I wish to know their kinetic energy. But how do you get them together? You will say, I'll get it separately. Because these are 3 different electrons, I'll get them separately. But is it feasible? Suppose in a metal I have got lakhs of electrons moving. Can I describe them separately? It's not possible. So I have to adapt a technique so that you can describe many particles together. Now the question is that if you think classically, what does it mean by many particles? You see, when you talk about many dissimilar particles, you see the example, a classical example of balls. You see, if I have got say 5 balls there, I can describe the motion of the 5 balls together. Okay, I can describe the motion of the 5 balls together. Okay, because I will say red is moving like this. You see the initial video, green is moving like this, blue is moving like this, orange is moving like this, yellow is moving like this. Okay, so you may say I can describe the 5 balls together. Okay, and now number is limited 5. So you can describe, you have got that advantage. But is it possible to describe say many, suppose I have got all red balls are there, next case, all are similar balls. Again, if it is 1 ball, 2 ball, 3 ball, you can possibly do it. Okay, now if you have got many balls together, what to do? Okay, it's all of them will be moving together. How do you describe that motion? Okay, so if you move from one particle to many particles, how do you describe the motion? So that is the area of concern. Okay, you can describe one object, you can describe 2 objects, you can describe 3 objects, but how can you describe many objects? So how do you describe the dynamics of many objects? Okay, in any mechanics for that matter, suppose I have got 100 red balls moving, there is also a many object problem. Can you explain, are you in a position to explain that situation? Can you describe that situation? That is a question. That is, I have got many objects moving together. Can you describe that situation? Are you in a position to describe that situation? That is the question, that whether we can do it or not. Okay, so let me do it in a proper way. Let me show you with an example. Okay, you will try to realize it. I'll first tell you what happens classically, and also after that I will tell you what happens in practice. Okay, just give me some time so that I can make you understand. Present it. Okay, you'll see it is beautiful. Suppose I consider this much. Suppose that I've got one black ball moving along x direction. So you see, you can easily describe that. Say at a given time it may be at x1 and it is reaching to some other position x2. So you can, after some time it may be reaching to some other position, say x3. So you are in a position to describe that situation. Now suppose I have got a blue ball moving. Again it may be at x1 prime. After some time it goes to x2 prime. Times are mentioned here. And after some time it goes to, suppose, to x3 prime. Now suppose I have got a green ball moving. So it may be at x1 double prime, this may be at x2 double prime, this may be at x3 double prime. So these are 3 different. Now if I ask you to now I would suppose I've got a red ball moving. Suppose I've got a red ball moving. Okay, so if I ask you to describe the position of the red ball also, you can do that. Suppose red ball is here at x1 triple prime, x2 triple prime,
x3 triple prime. So 3 balls are moving. So 4 balls are there. This is ball case 1, case 2, case 3, case 4. Now it's a many particle case, but still you can describe the motion of the black ball separately, blue ball separately, red ball separately, and green ball separately. You can do it easily. So because number, what is the point? Here number is less. Okay. And second point is that that's why we can describe them separately. So my classical mechanics works well. Okay. Now suppose instead of these 4 different balls, we consider another case. We now consider this case. We now consider this case. If instead of 4 different balls, we have got lot of gas molecules moving in a container. Molecules of gas moving in a container. You know, in 1 mole, 10 to the power 23 numbers of gas molecules are there in 1 mole. And you know, by kinetic theory of the gas, if you keep it at a temperature T, any gas molecule should have 3/2 kT amount of kinetic energy, and they move all randomly. If it is moving in this direction, this may moving in this direction. Say all of them move in random motion, and their numbers are enormously high. Okay, their numbers are enormously high, very large. Question is that all of them, suppose I have got 2 types of gas molecules there. One is colored red, another is colored blue, a green. Okay, now you may say I've got, you see, I've got 2 mixture of gas molecules. Now the question is that how do you describe the motion? What is the problem? Problem is that many particles are moving. Okay, understand, many particles are moving. Understand? So the idea is that it is difficult for us to describe. So that means for many particles, we have to do something. 2 problems are there. This case was the many, I have got 4 objects moving. Number of objects were less. Okay, number of objects were less in this case. Okay, number of objects are less. I have got 4 objects moving. Number of objects are less, only 4. But advantage is that these are all dissimilar objects. Another case I have shown you dissimilar objects, but both of them are many. Okay, many objects are moving. So here 2 types of problems are there. Number is large, and 2 different type of objects are there. Now I present a third case. Suppose I have got only 3 objects moving. I have got only 3 objects moving. Suppose this is one ball 1, whose coordinate may be x1. This is another ball whose coordinate may be x2, and this is another ball whose coordinate may be x3. Now you tell me, if you have to describe the ball, all of them may be moving along this arrowhead. Your problem is that you cannot identify which one is 1 and 2 or 3. So that means if you have to describe the ball, you have to describe them together. All are similar. All are identical. So all are identical and indistinguishable. You cannot distinguish them. On the contrary, this case is that all are identical, all are balls. These are identical, but you can distinguish them. So we are talking about those situation, the case of many objects studied in statistical mechanics, which is applied for many objects. And this is the case of identical and distinguishable objects, which you can describe separately. So no problem as of now. Now this is a bit difficult case. Here I am talking about the identical and indistinguishable object. You cannot see the matter. You can see the matter, but they are indistinguishable. All are similar. So if you have to describe this system, in the previous case, you could be specific. Say in this case, you could be specific where balls are. Here you can be specific. Black is there at x1. Okay. Okay, blue is there at x1 prime. Okay, green is there at x1 double prime. So you can separate, these are separate object, you can separately measure this. Okay, red is there. So you can describe them separately how they are moving. But that advantage is lost here. You have to describe all the particles together. You have to describe, because all are green balls. So you have to tell them on an average, these balls are between x1 to x1, x3. So they are distributed between x1 to x3. So on an average, they are located here. So that is something we are talking now. Okay, they are between x1 to x3. Here I am not specific. I am telling in between x1 and x3, all the balls are located. Okay, so this is something we are talking about. That is the average value in quantum mechanics. So where they are lying on average. Okay, so this is this window is the on an average the position of the particle on an average where the particles are there. Okay, in this case balls, they are present on an average over this region. So that is something we are talking about. Now the problem is that I am not concerned about balls in my class. In my class I am talking about microscopic electrons. So how do you calculate average value for electron? Because you can see a ball, you can at least predict they are between this, as I show in the initial videos, the balls in my hand. At least you can predict that they are, you can see them, first ball, this ball, you can see them and you can at least say where they are. By your naked eye, you can see the ball and you can do the actual measure. Actually, you can directly, you can see those ball and now you can conclude they are between x1 to x3. But in this case, in a quantum mechanics problem, we do not discuss about balls. In a quantum mechanics problem, we talk about electrons. Our main concern is about electron. Suppose I have got 3 electrons moving. This is electron, this is also electron, and this is also electron. 3 electrons are moving along x-axis. So the wave function of this electron may be like this much. So the probability of finding the electron, if psi is the wave function, is highest at the point x1. For the second electron, suppose this is the wave function of the electron. So suppose this point, if I just elongate it, suppose this point is x1 plus delta. So probability of finding the electron is highest at x1 plus delta. Okay. Now I consider the other electron. This is the wave function is also psi, because if it's all are electron, all should have same wave function. Now I considered another case. Suppose for the third electron, suppose that this is the third electron. This is also electron, wave function is same, and you can see the probability of finding the electron is highest here at x1 plus delta maybe say x1 plus 2 delta. Okay, so what you have to say, electrons are on an average. I cannot be sure here what exactly electron is, because all to me which one is electron 1 and which one is electron 3 I do not know. Okay, if they interchange their position also I cannot realize. Okay, so I'll say on an average electrons are distributed between x1 to x1 plus 2 delta. So average position of the electron is between x1 to x1 plus 2 delta. Question is that in a quantum mechanics problem, this value you have to get it from psi, because psi knows everything. So we now discuss how from psi you can get this average value, because this is just a graphical representation. To make you understand, I have shown you it graphically, pictorially. So now let me tell you how from psi you can calculate it. Now psi is a function of mathematics. So get it from psi, you have to use the operator, corresponding operator. Now the related operator, so if you have to, suppose in this case, if you look at this example of this electron, say this is electron 1, electron 2 and electron 3. So if these are their wave functions. And I'm telling all are electrons, so all of them have got the same wave function. So this is x1, this is x1 plus delta, okay, and this is x1 plus 2 delta.
So electrons on an average are located between this region. Now so whose average value I wish to know? I want to know average position of the electron. So I am expecting the average position of the electron by this way. So that's why this is called expectation value in quantum mechanics. So this is represented by the operator, in this case position, like this. This is the new representation of the expectation value. Okay, who knows this value? Psi knows it. So the formula of getting it from psi is this much. You can get it from psi by this way. From psi, you can get it from this way. Okay, so average position would be, you write down orthogonality formula in the numerator and the denominator. Now these are all electron, so all of them have got the same wave function because I have got 3 electrons. So electron 1, this is the wave function of the electron psi. This is the second, next electron I have shown you, x1 plus delta. Its wave function is also psi, and this is the other electron I have shown you. Its wave function is also psi. Okay, this is x1 plus 2 delta. Okay. So all the electron has got the same wave function psi. So to write down orthogonality relation is for same function. M is equal to n case. All the electrons are same. So psi star psi dx. What you do now, the corresponding operator you put here. So this becomes the formula of getting average value. So this becomes the formula of getting average value in quantum mechanics. Now, if you look at the idea here, the denominator is nothing but 1 by normalization condition or by orthogonality condition. This is nothing but the normalization condition. So you can write down for normalized wave function, this formula will be only restricted to this much, numerator. So again, it is an integration, but this is the formula. Okay. So you can write down, I have done it for x. You can express it for any operator. Okay. For any operator in general, for any operator O, this can be written as this much, minus 2 plus infinity psi star O psi dx. And for normalized wave function, denominator is 1. This is for normalized psi. This is the formula. And the examples that will be given to you for expectation value calculation usually comes in examination. So here their denominator will always be 1. Just let me show an example to you. How do you calculate the average value? The calculation of average value. Okay, one little example of calculation of average value. Suppose I have been given a psi is equal to root over 2 by a sin pi x by a. For the value of x lying between 0 and a, and this is 0 elsewhere. So you have to, my job is to calculate the, suppose average position, that is x, this one, and average momentum, that is average p. So I wish to know these two data. Who knows this data? Psi knows it. So answer is that, ask question to Psi. Okay. So let me see what is the response of Psi. Now to answer this question, first I have to plot the wave function. Okay. If I plot the wave function, it looks like this much. X equal to 0 to x equal to a. Okay, it is like a sinusoidal function. If I plot the wave function, psi is equal to root over 2 by a sine pi x by a. And beyond this, that is a to infinity, psi is 0, and minus infinity to 0 also, psi is 0. I consider this. So if I have to calculate the average value of position, then I have to do this integration, minus to plus infinity, psi star x cap psi dx. So you can divide the limit into three parts, minus infinity to 0, psi star x cap psi dx, 0 to a, psi star x cap psi dx, plus a to infinity, psi star x cap psi dx. So as you can see there, for this minus infinity to 0 is this region 1 where psi is 0. And a to infinity also, here psi is 0, because this is basically this region. So our problem is our average value calculation is restricted only between 0 to a. So if your psi is basically root over 2 by a sine pi x by a dx, x cap is x, and psi star, if psi is this much, psi star will be equal to root over 2 by a. Sine function is a real function, sine pi x by a. Root over 2 by a, root over 2 by a makes it 2 by a, 0 to a, x sine square pi x by a. This is 2 by a. Now I can bring in 1/2 here, 0 to a, x 2 sine square pi x by a dx. So this takes a form 1 by a, because 2 will cancel, 0 to a, x 1 minus cos 2 pi x by a dx. Integration of x cos will be 0 by orthogonality condition. So integration of x dx will be s square by 2. So this will be 1 by a into s square by 2. So the average position of the particle will be equal to therefore a by 2. So it's on an average, if you've got more particles are moving, average position would be a by 2. This problem will come on later on also as a part of one of the problems of quantum mechanics, so that you have calculated. That means if I have got, suppose, over this region lying from x equal to 0 to a, if I have got suppose 10 electrons moving, on an average their position would be equal to a by 2, and you can see this through this graph also. Here psi square is maximum, so average position should be a by 2. Okay, this is on an average. This is the average position of the particles. Now let me calculate the average momentum. So what should be the momentum of these 10 electrons when they are present here? This is minus infinity to plus infinity, psi star p psi dx. So as I did just now, I will divide the limit into parts. So it will be minus infinity to 0, that is this region. Okay, psi star p psi dx, that is 0 to a, psi star p psi dx, plus a to infinity, here also psi is 0, psi star p psi dx, this is 0, this is 0, this will be 0 to a. Now psi star, as you know, it will be root over 2 by a sine pi x by a. Operator form of momentum is minus I square del x, and psi will be root over 2 by a sine pi x by a dx. Now you know this will be like this much, 0 to a, 2 by a sine pi x by a. Sine function on integration will give you cos function, so there will be minus I squared, okay, pi by a cos pi x by a dx. Okay, So basically sine and cos on integration will give you 0. So the average momentum of the particle will be 0. So this is the problem. So if the particle moves here, these electrons are moving here, these 10 electrons. So their average position should be a by 2, but their average momentum should be 0. They will, on an average, they will not be moving from at that position. Now another problem I just do in front of you of average value calculation, that is also is a very common and popular examination question. Suppose my psi is given as Cx. For the value of x lying between 0 and a, and it is 0 elsewhere, okay. So therefore, if I have to ask to calculate the average position, their answer is that my first job is to plot this wave function. If you plot it, it will be looking like this much. It will be Cx between 0 and a. Minus infinity to 0. The psi is 0. A to infinity also psi is 0. So result of the average value calculation, minus infinity to plus infinity, psi star x side dx. So it is minus infinity to 0 x psi dx plus 0 to a psi star x psi dx plus a to infinity psi star x psi dx. And as you know, this is first term is going to be 0 because psi is 0 in the region 1. Last term will also be 0 because psi is 0 in the region 2. So your entire problem is only limited from 0 to a. Psi star psi is Cx, so psi star will be C star x. So it is C star x. Average value of x cap operator is x, Cx dx. So C and C will make it C square, mod C square, C and C star. 0 to a x cube dx. So the average position will be mod C square x to the power 4 by 4. So this is the formula of average value of the position. So I have done few problems for you. Now let me get back to the sharing again, my PowerPoint again. If you look at the PowerPoint now, so I have solved some problems in front of you. This is the formula. Please look at this. This is the formula of average value calculation for any operator. Okay, this is going to give you by normalization condition. You are happy only with the numerator. So knowing normalization condition is very important. Okay, remember it. You put two operators in the correct operator in between. Okay, so that will give you the value. This problem just now I have done in front of you. So okay, it is a by 2. Average momentum is 0. So now we will now summarize all the whatever I told you till now in this class. We will now make a summary of that. First point is that you see in quantum mechanics, you see this is last time I am making a final, I am just repeating the whole story. In quantum mechanics class, okay, we'll now make a final summary of whatever I have been discussing so far. I've been shouting about. Every day I shout the basic variable in quantum mechanics is wave function psi with psi square, giving the chance of finding the particle. Psi has got no meaning, it's a mathematical function. The dynamical variables are obtained by using called operator are represented as represented operators in quantum mechanics. Any dynamical variable could be variable is wave function psi. Psi has got no physical meaning, it's just a mathematical function with mod psi square giving me the probability or chance of finding the particle. Based any dynamical variable like of motion, any parameter of motion is to get, I have to get the corresponding operator. So variables are represented as operators in quantum mechanics. The operators satisfy eigenvalue equation. If an operator is O, you have to get it from any information from the function psi. So as if the idea is that all information of motion are stored in psi, satisfy an equation called eigenvalue equation. So you'll act on psi, give you back the function multiplied by the constant. Then you satisfy eigenvalue equation. The constant is a measured value of the dynamical variable. That will be a structure. You have to put the actual numeric values. That's like momentum is like h cut square k square by 2m. Sorry, momentum is like h cut k. Kinetic energy is like h cut square k square by 2m. So in a problem, you put the value of h cut k or m to get the numeric value. So you'll get the quantum mechanical version. This is the formula of average value, which I just told you. Now there is a fifth point also. You know, the wave function psi you can obtain by solving Schrodinger equation. Now Schrodinger equation solution is a mathematician's job, solving a differential equation. Now the question is that after solving the differential equation, you will get psi. Now after you get psi, what you will do? You have to do many things. From psi you can generate the whole mechanics. But whether any psi will be acceptable to you or not, it depends on one condition, that is called acceptability of the wave function. Wave function has to be well-behaved function. Now, this well behavior is not human well behavior. It is not our well behavior. It is Ruppok-Serre's well behavior. According to Ruppok-Serre, well behavior means a mathematical function should have this much of quality. This is mathematical well behavior. It has to be single valued. It has to be finite because it is representing a matter. Matter is not infinite. Electron, finite, single valued. It should have only one value at a given point. Analytic means first and second derivative will exist. That means wave function is continuous. Same matter, so same wave function continuity will be maintained. So if it satisfies this condition, then and only then it is an acceptable wave function. So when you'll be solving Schrodinger equation, you have to judge it. Okay, any arbitrary function cannot represent a matter. I'll tell you, I'll let you know with some real life example. Okay, how do you calculate this actual? How do you judge whether an function can represent a matter or not? So we'll do it, but it's better we do it in the next class. Okay, we'll do it. It is going to be a very wonderful and short journey there. We'll do it. Now, these 5 points together, you should keep it in mind. They are called postulates of quantum mechanics. So basically, it's a summary of everything that I taught. Okay, so if somebody asks you to write down the postulates of quantum mechanics, you should write down these 5 points. Okay, and you note here, excepting the last one, this fifth point, acceptability of function, all 4 are well discussed with the relevant problem. Okay. So we are somewhere there, I think, to penetrate the actual problem of quantum mechanics. So very soon we will do that. But let us learn in the next class about whether an wave function will be acceptable or not. Okay. So wait for the next class. Thank you for the time being. Okay. So this is something we will discuss next day, acceptability of a function. We will be discussing it in more detail in the next class. Thank you.